So when creating a wind turbine or a generator, the big question is, how do you know which motor would make a good generator? How do you know what to do in order to go around building your own generator? It's a very common question. Unfortunately, there are some things that you need to understand before being able to make those decisions, and in this video we talk about the theory, then I give 3 examples to illustrate that on devices that you can make yourself. So it is a bit long, but stick with it because some of this stuff is absolutely essential. Now, right from the start, motors and generators are the same thing. So we've big mystery. Why is it when you put one motor in a wind turbine it does great, and you put a different motor in a wind turbine it does pants? Well, there's a very good reason for that. We make motors because we have different jobs they can do, and a motor is defined by its active length, the diameter of it, the number of turns and winding in there, and the power of the magnetic field. Because you put a current in there, you give it a kick against the field, and it's going to turn with a certain amount of power. Usually, bigger the motor, more turn it's got. Smaller the motor, tends to turn faster, but less power in the turn. When I say power, I mean turning force, which is torque. So it would be handy to know some stuff about motors so you could make some decision about what would work in a wind generator, or if you needed to make changes to your generator so a different motor would work, you could make those changes. Now obviously we work a lot with scrap motors and motors we find, because let me say it again, motors and generators are the same thing, particularly with DC permanent magnet motors, which is what I've got here. It's a treadmill motor, incidentally. They're just identical. Now the 3 things that are jolly handy to know are the speed constant, the torque constant, and the generator constant. And of course there's that magical word there, constant, which means they are constant. They don't change. You can get the speed constant really easily. And for the purists, incidentally, the SI unit for speed and the one I'm just going to use here are different. It uses radians in SI and we're just going to use RPM. But you find different manufacturers using different values anyway, so that can be a little bit confusing. But when we look at a motor plate, it'll tell you the voltage and it'll tell you the maximum speed. This one, 180 volts at 4,200 RPM. So if I bang in 180 volts, that's going to turn at 4,200 RPM, to be honest, more or less. The reason it does that is because, of course, a motor has a back EMF. Faster it turns, the higher that EMF gets, until the back EMF reaches the input voltage, in which case adding more doesn't do anything. And so it has a maximum speed. But anyway, at 180 volts, this will turn at 4,200 RPM. Divide one by the other, and you will get the speed constant. So we can say that more or less that 1 volt will turn this at 10 RPM. It's not right, it's more or less right, okay? So that means that if I stick a volt in here, we'll get 10 RPM. 2 volts, 20 RPM. 3 volts, 30 RPM, and so on, because it's a constant. The generator constant is the inverse of the speed constant, which means if I turn this at 10 RPM, I'll get a volt out. 20 RPM, I'll get 2 volts out, and so on. So we can work out the voltage that we're going to get out for the RPM that we put on here really easily using the speed constant. Now let's set that up and have a look at that happen. Okay, I've connected an open circuit, we've got it reading volts, and let's give that a spin. And there you go, the generator constant in play. I can get 3 volts out of that, turning it at about 30 RPM. So I've got it set up to read amps, and this time I've closed the circuit. I've connected the negative and the positive of the motor together. If I give that a spin, we get about 160 milliamps or so, and it's tough to turn. You can feel the effort required to turn it. Now that turning effort, of course, is torque, and that's measured in Newton meters. So the torque constant is Newton meters per amp. What that means is every amount of fixed force I put on there is going to generate so many amps at the speed at which I'm turning it. In order to turn it faster, I'm going to need more effort put in there. And you can feel it if you link that up and do it. Now, these kind of high torque motors usually have a very high resistance. This one's about 5 ohms or so, which is pretty high. something has a high resistance, it means that it's very susceptible to load. So if we swap this onto the voltage, leaving it in closed circuit, remember we got about 3 or 4 volts at that range, and if I give it a turn now, we're hard pressed to get about 0.2 of a volt. So the voltage drops off dramatically, and that's a common thing that happens with high resistance, high torque motors. Okay, let's have a look at a graph of that, because what's life without a graph? Let's say voltage here and current here, and if we take our voltage that we got when it was open circuit and our current got when it was closed circuit, it creates a line. And this is called the voltage current graph, and it looks just like a speed torque graph. This is for a fixed number of rotations, okay? If we take another area from here to here, remembering our V equals IR, that there is the power that the thing will generate, and it's normally about halfway down that line. If we increase the speed, then this line will move out in that direction, and we'll get another power area like that. And so power is related to the square of the speed. Now, when I said that this looks like the speed torque, obviously the voltage is taking place of the speed, the torque takes place of the current, or vice versa, and the gradient of the line is the resistance of the whole thing. Okay, I think that's cool to know. I also think it's very interesting, but of course it begs the question, what use is it? Most generation applications actually turn relatively slowly, far less than 1000 RPM. Most motors turn much quicker than that, sort of the 2.5, 3000 RPM range, and so there's a mismatch very often. Now you can correct that mismatch by using gearing, which is exactly what we did. And the same ideas are going to apply with gearing in terms of the ratio of the speed to the torque that you're going to suffer when it comes to running up a few gears. But you can increase the speed of that you spin a motor at by using gearing. So a high torque, low revving application can be matched to a high spinning motor by the use of gear of the gearhead. It's not something that's very often done with wind turbines, for example. It's pretty common to bolt the blade straight onto the motor, and it's probably one of the worst things you can do if you're using the wrong kind of motor. What you want is a high torque motor. Of course, you suffer from that voltage drop that we saw. There are other things you can do with it, and we have been exploring some of those other things in the video. Now, a quick word about efficiency. The efficiency of this thing that you make from scrap motors is extremely unlikely to be affected by the motor. The efficiency is going to be mechanical. It's going to be how well you make that structure that you attach to the motor for it to become a generator. I went down and bought one of these. It's a 200 watt hand blender from my local big box store, and it cost me £5.50. So as a blender, don't expect miracles, but when you take the blender apart, what you'll find inside is a DC motor and a rectifier bridge, and obviously an on-off switch. I mean, it astonishes me actually how they can make these things for those kind of prices. But that's the blender body itself, and in there is that DC motor. Now that DC motor is a 240 volt DC motor meant to turn in the region of 8,000 to 10,000 RPM. So the RPM per volt is going to be relatively high, but they spin really easily. So it's going to be millinewtons meters actually. So the millinewton meter per amp is going to be really low. You're going to be able to feel there's a lack of torque. So you can expect quite high voltages but very low torque. Anyway, let's get this motor out and have a look at it. So 4 screws, 2 at the top, 2 at the bottom, took this to pieces. And there's the motor's little drive spindle there to connect to the chopping blade. Here's our circuit board, that's a bridge rectifier, and then we've got our input. So we get a bridge rectifier, a switch, a whole load of cable, and this beautiful motor, all for £5.50. It just astonishes me. Anyway, that motor just lifts out. Okay, I've got the motor out, there's the meter. Now, given that this is about 10,000 RPM at 230 volts, we can expect quite a voltage on that when we spin it, so let's have a look. Look at that. Spinning it the wrong way for a start. So I'm easily getting anywhere between 1.5 and 7 volts by spinning that by hand. And we'd expect that given that the speed constant is so high. However, I'm spinning it by hand and I can feel that the force required to turn that is tiny. So we can expect the amps to be pants. Hey, that rhymes! Let's set it up for amps. And there we go, about 1 milliamp. Well, that's not bad. Anywhere between 1 and 11 milliamps is what I can actually generate from that, which is really poor. But then, as I say, you can feel that. Now, in order to make that useful, what it means is we're going to have to put a gearing system in. This bunch of pulleys, now they're really easy to make. They're just a couple of discs of wood, got a groove cut in them, glue one on the other, drill a hole and stick some bearings in, you'll get some pulleys. And there we go with our pulley arrangement, big, little, big, little, big, little. I've just put it in a cradle and I've got a couple of bolts on here. I tighten those bolts and it tensions the belt. Now, if I do that spin up, we'll be able to light that light. There we go. And we're generating about 26 volts while we've got it under load. If we have a look at the amps it's generating, oops, just put it onto amps. Now we're generating about 60 milliamps at around about 26 volts, so it's roughly 1.5, 2 watts, somewhere around about there. Okay, so I've got this bike upside down. Now the ratio between the little wheel and the big wheel is about 16 to 1. Ratio of this cog to this cog is about 3 to 1, so we're getting about 48, 50 to 1 gear ratio. However, this is somewhat better made, even though we've got a friction attachment here, and I'm able to put much more speed into this. Now the thing about these generators is the faster you can get them going, then the more power you get out, because the voltage is related to the square of the speed. So we need the gear ratio so that we can actually get it to turn quickly. We need good construction so we can input at a fast speed, and it has a dramatic effect. So I've got the voltmeter on. It's under load of this LED, and don't worry, you'll see the LED fine. And if I actually spin this up, we get a good old 30 volts out of that, no worries at all, and we get a really bright light because I can put some speed in there. Now if we have a look at the amps,
0.5 of an amp, 0.6, 0.7.
That's actually a 21 watt generator that we've created. So what we're going to do is use this flywheel with a different motor arrangement and see what we can construct as a generator. Why not? Now I not only have the flywheel, of course, because we do an awful lot of work with these kind of things, I have this kid's bike found by the roadside. So it's rusty, it's steel, which means I can chop it up and weld it to stuff, which is kind of awesome. And that's exactly what I'm going to do. We're going to remove the rear wheel, replace it with this because I modified it to fit in a bike, chop this up a bit, weld it around and make ourselves a flywheel generator. So let's get this chopped up. Okay, so there's the frame stripped out, and of course it fits rather nicely on this wheel. It's no surprise I did the wheel modification in a different video. And I'm thinking about how to put that. That's kind of nice, because it keeps this section here, so actually making a turn handle or a pedal or something like that would be really easy, because the relationships are kept. And that means chopping off here, here, welding it onto a base, and then putting a stay in there, which I can weld in, obviously. So I favour that, but I could have gone that way, I guess. There's always a load of ways that you can do these things. Anyway, I'm going to preserve this entire back end with the pedals and chop these bits off and clean it up. Okay, so I've got this bit of frame here from a treadmill actually. Now I tend to do this a lot. I look around for bits that I've got because all I've got to do is chop these tags off here, and I'm going to get myself a nice square frame to weld everything to. So it's going to be a piece of cake. And often I try to do that. I try to use bits I've got lying around, have a look and think about how they're going to fit, do the slightest modification I can just to get the bits that I actually need that I can then weld together with my rough and ready welding. Anyway, let's chop off these tabs.
Okay, so I've chopped them out, cleaned them up a bit. Now I can weld that tab on there. Then I can weld that bit of bike onto here, and the two tabs that I cut off I can weld there and there to act as like extra supports. So let's weld that together. Now we've welded our frame together, the flywheel just drops straight in to where the bike dropouts used to be, right there. So that's where our flywheel goes. And let's try that again. There we go. That's where our flywheel goes, right there. And of course we've got this, which is square to that, so we can put a cog and crank on there, and it's going to spin that flywheel beautifully. A little to this thing, and there it is bolted back together. I chopped off the pedal on one side, left it here, chopped the pedal down to make a crank handle, so I can turn that, it'll turn this, connect the chain, and of course it's going to turn that. Now the gear ratio is 2 to 1, so every one turn of this, I get 2 turns of that. As this is all about speed, then that's obviously not really very acceptable. It would be much nicer if I could up that gear ratio, and I do have this thing, which is a cassette. So if I unscrew that, I can remove that whole gear chain like that, and then I can replace one of the large gears on one of the small gears back on that cassette. Fit it in there, I can drive the small gear with this and use that large gear with this, and then I'll get a step up gear ratio, and it'll be in the region of 5 to 1, which is not brilliant, but it's a lot better than it was. So that's what I'm going to do. So welding in a couple more dropouts means I've been able to put that in there. Now all I did to swap those cogs around was unscrew it and swap the cogs, using the spacers, bolt it back together into those dropouts. So when I put a chain between this one and the small cog here, I'll get a 2.5 to 1. And then from this big cog here to the actual drive cog, I'll get another 2 to 1. So instead of being 2 to 1, it's now about 5 to 1. Now it could do with being better than that, but that's the gears I've got, so that's what we're going to go with. Obviously, if you change that gear ratio, you'll get a faster speed out of here, depending on your gear ratio. Anyway, all I've got to do now is connect some chains up, so I'll do that. Okay, and there it is with its chains on now. It cranks up really cool. There's a bit of a rumble because I used an old freewheel, which is a shame, but if I get that going, for a good few minutes, but it's a flywheel generator. Now obviously what we want to do is connect it to something to see what it's actually producing, and what we're going to connect it to is the same motor that we've been using in the previous videos, so that we get some kind of yardstick. So here is my little food blender motor that I bought for £1 and that I used in previous videos. Let's get that connected. Okay, so I've used a drive belt to connect it to the exact same motor we used in 1192, because what we're interested in, remember, is the relationship between speed and voltage. And this is about 28 centimetres, that's about 2 centimetres, so we've got a 14 to 1 gear ratio, we've a 5 to 1 gear ratio here, giving us around about 70 to 1. In 1192 we tried 1 to 1 going up to about 20 to 1, and we saw that the voltage started off really low and actually shot up, so that when it actually rotated quickly we're getting about 20 watts out of it or so. Now I have actually changed what I've got the load. This load is an LED lamp that will only begin to light at around about 200-220 volts, which is crazy. But let's give that a go. We'll spin it up and we'll see if we can get that voltage out of it. Oh, the meter's right there. We got about 250 volts out of that, which is madness if you think about it. Because an LED lamp like this isn't actually a purely resistive load. So what I've done is I've stuck a soldering iron on it. A soldering iron is just a heat resistor. So let's give it a spin under a pure resistive load. 145 milliamps. Now let's try the voltage on the resistive load. Set it up for volts, spin it up and see what happens. Volts, 150 milliamps. That's actually getting warm. Okay, I mean, I'm impressed with that. This little motor, if properly set up and is a 70-1 ratio, will give us 200 volts and we're getting about 30 watts out of it. If you think about it, that's incredible. So the whole point of this video is to illustrate the difference that speed will make. Now obviously it's a bit of a workout because also torque goes up. But I thought I would go through that, extend it a little further to see what kind of voltages you can in fact get from these tiny motors. I hope you enjoyed the videos and thank you very much for watching. Oh, please do remember to subscribe.